Okay, we're starting 3-2 day 2. I'm going to spend an extra day here because this section and the next one, once you get both of them going, they get a little confusing. So we'll do a little extra practice here before we move on. So the first part of the note is just going to come right from this worksheet, using these contingency tables. And if you look at this first one, just reading the table, we've got education and salary of employees. So we've got people with less than a high school education, broken up into 3 categories: under 20,000, 20 to 30,000, and over 30,000. Then you've got high school education broken up, some college people broken up, and then a college degree. And then the totals going this way. And I added all the totals in just to save us some time. So we're going to be randomly picking one person from this group of 1,205, so that is our sample space, if we aren't limiting it. So you have to pay attention to the question to see if it's limiting the sample space. So here it says, what's the probability that the employee we pick has less than a high school education? So nowhere in this question did they limit us down to any one particular group. So we are looking for a less than a high school education. And if you look, there's 69, 36, 2 for a total of 107 of them. So I've got 107 chances out of the 1,205. And I'll just leave the answer as fraction. Okay, the next one is the probability the person you picked earned under $20,000. So we've got to see how many people earn under 20,000. Well, those people are right here: 69, 112, 102, 13 for a total of 296 out of the 1,205. Now for part C, here we can make this challenging, or because it's a table, it's actually very easy. What's the probability that an employee earns over 30,000 and has less than a high school education? Now yesterday I said when you saw the word "and," you had to multiply. So I want to do it the old way from yesterday, but then show you really don't have to when it's a table like this. So let's look. If I was to do this the long way, just to show you, it would be, because of the "and," I have to multiply. So it's the probability that the person earns over 30,000, then multiply that by the probability that the person has less than a high school education, given that they make over 30,000. So that's two probabilities that I'm going to multiply together. I'm going to move up to here where there's more space for this one. So the probability that the randomly chosen person makes over 30,000, I'm not limiting the sample space, so that's just this whole column, which is 404, out of the 1,205. Now the second probability, because there is a condition on it, I am limiting it to less than a high school education, given that I'm only looking at the over 30,000 people. So that means we're going to cover up these two columns. The over 30,000 is here, so now my sample space on this one is the 404. That's my bottom number. And I'm looking for less than a high school, that's 2. Now if you see what happens, the 404s cancel out, and I get 2 over 1,205. And that was a lot of work. And you don't have to make them that much work when we've got these contingency tables. Because the way to get it quickly is just to say, I'm going to look for the people that have both of these things going on for them. So they make over 30,000 and they have less than a high school. Over 30,000, less than, it's these two people right here. So it's just this one cell out of the total. So you really don't have to go through this multiplication one when we have the table. Just go for the one cell that has the two conditions over the total sample space. So we'll do that here on this one. What's the probability that an employee earns under $20,000 and has a college degree? So we are not limiting the sample space, so right away I know it's going to be 1,205. But now I want the one cell that has both of these things going on. So under 20,000 and college degree, 13. Okay. Now E. Given that the employee has only a high school education, that means I'm only looking at this group of people. We are limiting the sample space. So I'm going to find where the high school education's at. That's this row here. So I'm only going to use those numbers across there. So my sample space is 224. I'm not going to look at any other rows in this table. Cover them all up. So you can't grab the wrong numbers. Okay? So given that the employee has only a high school education, find the probability that the employee earns over $30,000. And I believe that's this last column, so 14 out of the 224. Okay, next one. Given that the employee earns over $30,000, so again, this given that phrase limits our sample space, so we're not using the entire table. So now over 30,000 is that column there. So I'm going to cover up these other ones and not use any numbers from them. So I'm only focused on the people earning over 30,000. Find the probability that the employee has only a high school education or less. So I got two groups here, high school education or less than a high school education. So that's these two. That would be 16 out of 404. So 16 out of 404. And I'm going to add one more here. G, we'll make it G, just because our SAT practice has had some with where they limit the sample space, but they don't use the phrase given that. So I should have left that one there. Find the probability that a randomly selected person, find the probability that a high school graduate, let's see, no, I want to say that a person with only a high school diploma earns $20,000 to $30,000. Okay. So I didn't use the phrase given that, but you can see I'm only concerned about the people that only have a high school diploma. So find the probability that a person with only a high school diploma earns between $20,000 and $30,000. So I have limited my sample space here by saying I'm only concerned about the high school diploma earners. So I'm looking at this one row again, and the 20 to 30, so I've got the 1,000 is 98 people out of 224. All right, and then number 2, all of these are, this is just using the notation without the words. So again, when we do this bar, that means given that, I'm only looking at the female. So we've got favorite leisure activities, a bunch of them, and then broken up by male and female. So this first probability question is saying, what's the probability that a person chose sports as their favorite leisure activity, given that they're female? So my sample space are all of the females. So right away, I know my bottom number is 334. And sports will be my numerator, so 39 out of the 334. This one's saying, what's the probability the person I pick is female, given that they chose sports? So the sports column is your sample space. So you go vertically to the sports and you use none of the rest of the table. And then the probability that that person is female is 39 out of 106 that chose sports. So this second part is your sample space. So this time, what's the probability that my person picks reading, given that they're male? So we're using the male row, which all of these people are males. So my sample space is 362. Reading is 76. And then here, so flipping it around, what's the probability that your person is male, given that I'm only looking at the people that chose reading? This is my sample space, the given that condition, reading. So I'm doing this column, sample space is 161, male 76 out of the 161. So take your time and talk yourself through those. All right, our next example here's some given information. The probability that randomly selected high school senior has a score of 500 or higher on the math portion of the SAT is 0.49. So if I randomly select a high school senior, the chance of me getting a person that has a score of 500 or more on the math portion is 0.49. So we are going to randomly select 3 high school seniors. And we're going to find some probabilities. First probability question, can you find the probability that all 3 have a 500 or higher score? Okay, so you have to be able to convert this into either an AND situation or an OR situation. Now I know we haven't talked a lot about OR yet, but again, how would I rephrase this? I would say I'm looking for the probability that my first person has that score, and then the second person has that score, and the third person has that score. So for me to say all 3, the first one, and the second one, and the third one, now that I know this is an AND situation, I know I've got to multiply those probabilities together. So AND, multiply. When we see OR, we're going to be adding, but that's coming in another day. So, and it's the same probability for each person. The sample space does not get reduced. It's always a 49% chance from the population. So it's 0.49 times 0.49 times 0.49, or you could have just done 0.49 to the third, and I'm not going to bother with the final answer here. You can save that stuff for homework. We care about process in the notes. Okay. Another question, same situation. What's the probability that none of the 3 people I select have a 500 or higher score? So, again, I'm looking for the probability that first person is under 500 and the second person is under 500 and the third person is under 500. So again, all 3 things having the same situation, that's an AND, I got to multiply. Now I didn't give you the probability for under 500, but it's just the other side of the coin. So if 49% got a score higher than 500 or higher, then 51% were under the 500. So it's just going to be 0.51 times 0.51 or 0.51 to the third. All right, and then the last one that tends to get confusing. What's the probability that at least one of the 3 has a 500 or higher score? Okay, at least one means I am looking for either one person or 2 people or 3 people. That's a big OR situation. There's a lot of probabilities to do there. So the best thing to do is the complement to that. If I'm looking for at least one, that's every single situation except for none of them having a score of 500. So when we see at least one, we're going to change that to the probability of 1 minus the probability of none of them having probability of 1 minus the probability of none for getting at least 1. It's always 1 minus the probability of none. And I just did the probability of none. So it's 1 minus this 0.51 to the third, because that was the probability of none of them having that score of 500 or higher. Okay, the last example comes from an old game show called Monty Hall Game Show, and they featured this in the movie 21, and I've got the clip on YouTube. It's pretty short, somewhat interesting, so if you haven't seen it, hopefully you're entertained a little bit here. But let's see how good I can do at
all right, now, let's
here.
give Ben a chance for some extra credit, shall we? We're going to call this the game show host problem, all right? Ben, suppose you're on a game show, and you are given a chance to choose from 3 different doors, all right? Now, behind one of the doors is a new car. Behind the other 2, goats. Which door would you choose, Ben?
Door number 1.
Door number 1. Ben chooses door number 1. All right, now, the game show host, who, by the way, knows what's behind all the other doors, decides to open another door. Let's say he chooses door number 3, behind which sits a goat. Now, Ben, the game show host comes up to you and says, Ben, do you want to stay with door number 1 or go with door number 2? Now, is it in your interest to switch your choice?
Yeah.
Well, wait. Remember, the host knows where the car is, so how do you know he's not playing a trick on you, trying to use reverse psychology to get you to pick a goat?
Well, I wouldn't really care. I mean, my answer's based on statistics, based on variable change.
Variable change? But he just asked you a simple question.
Yeah, but you changed everything.
Enlightenment.
Well, when I was originally asked to choose a door, I had a 33.3% chance of choosing right. But after he opens one of the doors and then reoffers me the choice, it's now 66.7% if I choose to switch. So, yeah, I'll take door number 2, and thank you for the extra 33.3%.
Exactly. People, remember, if you don't know which door to open, always account for variable change. Now, see...
Okay, I have no idea how that showed up at all. I couldn't see my computer screen anymore, but hopefully you got the gist of it. So I want to talk about through that game. If you haven't seen that movie before, it's great. It's 21, true story. About some really smart math people that got themselves in trouble. But anyway, let's talk about this situation for a minute. So it was the Monty Hall Game Show. And what the situation was, there were 3 doors. Behind one door was a car, and then behind 2 of the doors was a goat. So, what the person would do was they would pick one of the doors, and then, because the Monty Hall knew where the car was at, and he knew where the goats were, he would open up one of the remaining doors, and it would be a goat. So then you had the option to keep your door or switch. And then the question becomes, does it matter whether you stay or switch? Is it equal probability on what's going on here? So we want to look at this situation. So if we make a little table of possible outcomes, stay and switch. So let's just say, we don't know, but let's say the car is behind door C. Alright, let's say you had chosen door A. Okay, so you pick A. I'll put a little block there. So, he would open door B, because there's going to be a goat here. Now you have the option to stay with door A, or switch to door C. So, you can see if I stay with my original choice, I'm going to be a loser, because the car's over here at C. So if I stay with A, I lose. If I switch over to C, I'm going to win. Okay, well let's say I had chosen door B instead. Again, the car's still over here, so he's going to open door A. There's going to be a goat, so now I can stay with B, or I can switch to C. If I choose to stay with my original choice, I'm a loser again. If I was to switch, I would have been a winner. And now the last situation is if I had chosen door C, which has the car, doesn't matter which of these two is going to open, they both have goats, so one of them's open. If I stay with my choice of C, I get to win. If I switch, I'm a loser. So, I can change these into some probability questions. What's the probability that I win this game given that I stay with my original choice? So here's my stay situation. There's 3 possible outcomes. I win on only one of the 3 choices. So I'm a 1/3 chance of winning if I stay. Well, what's the probability that I win given that I switch? Okay, so I'm limiting my sample space to switching. Well, if I look here, I'm a winner 2 out of 3 times. I've got a 2/3 chance of winning. So, if you have the option, you would want to switch at the end. And if you can think probabilities also. If you first start the game, when you pick, you've got a 1/3 chance of picking the car, which means there's a 2/3 chance that the car is out here. So when he eliminates one of these, the remaining door still has a 2/3 chance. That's that variable change he was talking about. So that's all I got to say about that one.